All right. So like I said, you will want to go ahead and print these out. It'll serve as help for you on your take-home test. But remember, whenever you see simple linear regression, we're calling that the line of best fit, the least squares regression model are all talking about the same things. Bottom line for this stats class, what you need to know is it a good fit? Is it a bad fit? Realize that we use the linear model to predict things, okay? So, regression line was computed using the least squares regression model. So if you're filling in, which talks about minimizing the deviations from every data point to that regression line. Model assumes that there is a line with a vertical intercept. We call that the y-intercept. And then sometimes that y-intercept makes sense in context, and sometimes it does not make sense in context. So it just depends. And then it also has a slope. Again, slope intercept. And we did it in, we called that the true regression line. And then what we did is, just like we sampled things and made predictions about the population, when we create scatter plots from data from a sample, we're using the scatter plots to fit a regression line to our data. Yes?
Hold on, what regression line?
True. Sorry. True regression line. And that's what I'm talking about right now. In reality, there is some true line of best fit. Now, is it going to be perfect? No, but in reality, it exists with all the data points out there. We don't have all the data points out there. We only have, that's slope, yeah. I'll try to make this smaller or bigger in a sec. We only have the data points from our sample to fit that line. So what we do is, the true regression line would be something like this. Y equals A plus capital BX. But what we do is we make our predictive model, and that's lowercase y hat equals lowercase a plus bx, where a and b are estimates based on our scatter plot. Does that make sense? Just like in before, we have the population reality. We called it mu, or we called it capital letter P. And then we sampled and we had a p hat, or then we sampled and we had an x bar, and we used that to predict stuff about our population. Same here. There exists some true linear regression line. Linear regression is the wrong word. There exists some true linear relationship based on all the data. But what we have is an estimate of that relationship based on our sample. Yes?
So you're saying that capital A plus capital BX is the true regression line?
And it's the equivalent of what that is, what mu is, and it would be the equivalent of what capital letter P is. Just like we sampled and got a p hat to estimate capital P, just like we have an x bar to estimate our mu, we have y hat equals lowercase a plus lowercase b of x to estimate the true regression line. Does that make sense for the relationship? And again, that's coming from our data, just like p hat's estimate comes from our data, just like x bar's estimate comes from our data. Okay. The last thing I need to add to this is this little letter E, and I'm going to add it right here, plus E, and I want to talk about that. Since that is a predictive model, since this is predicting what the reality is, it should make sense that sometimes my prediction will be a little bit higher than what it's supposed to be, and sometimes my prediction will be a little bit lower than what it's supposed to be. And how far our predictions are off, we would call that an error. And to pull a word back from long ago in a galaxy far, far away, we looked at that error part as a residual. Calling back the Wayback Machine. Residuals are actual value minus predicted values. It's how far away an actual data piece is from that predicted value. So I'm just quantifying it here as E, saying my error may be above, it may be below, but tacked onto any estimate, we do have some error. Does that make sense? Okay. Assumptions about the error. I don't really need you to memorize. I haven't seen them test on this on the AP exam. I just want to talk about it here. Distribution of E at any particular x value has a mean of 0. I'm going to put this in context in just a sec. That's just to say the average of all the errors is 0. That's a mu of errors, or the mean of the errors is 0. Mu error, the average of all the errors is 0. Standard deviation of E is the same, and we will use this kind of later on today. The standard deviation of E, which is standard deviations of the errors, does that make sense? For any particular value, it's the same, and we denote that by sigma, which is fine. And the big connection piece is the errors around any x value are normal. Okay? So we have a normal distribution, and what I want to look at right now is that fourth one, and it says the random deviations associated with different observations are independent of one another. If you look, please, just at parts 3 and parts 4, remember when I talk about assumptions or justifications as why you're doing what statistic with what statistic? Usually it's the big 3, random, independent, and normal, correct? What do you notice about here? Distribution is, and random, and notice that the big 3 are showing up here. Random, independent, normal. Those assumptions kind of check through for everything that we do. It's just what is sufficiently large for normality. Did it say it's random, or do we have to assume it? Is it independent? Now what this is saying is, I have a picture of it. I think the next slide I have a picture of it. It's a lot easier to see on a picture. Not that. Here. Okay? This is what I'm talking about for that error being normally distributed. Here's a value. I know it's hard to see print-wise, but we have a value of just an x, and then I know I plug it into my linear regression model, which is y hat, again, is a plus bx. That's a predictive model based on my data, and so I will have a predicted y value here. That's the y predicted with this value of x. For that value of x, we may or may not have an actual y data point. Remember on our linear regression models that are all around the classroom, you guys have x and y values. Those are actual data pieces. I might try to predict something at an actual data piece, or I might not. If there was an actual data piece there, we would call that, we could calculate a residual. Does that make sense? Now, if there isn't a data piece there, we know that we are going to have a possibility of that error. And that error can be above my estimate or below that estimate. But if I have the standard deviation of that error, I can figure out how far away my estimates may be. So for any given x value, I have this normal behavior about the y. This normal curve that you see here is talking about the predicted y values based on the standard deviation. Does that make sense? Yes or no? Because I feel like, this is hard stuff, but hopefully you guys are connecting these ideas. Can I clarify yet before we move forward? Because these are kind of the connection pieces that we're going to need to go into next week. Yes?
So just to make sure, the normal curve is all the y values you can
That
get?
could be predicted.
Yes, it's talking about the predicted y values and how distributed they are amongst that. Yes?
So the normal curve is kind of like the range of the residual, is that?
That's another way to put it. Yeah, it could. It's a possible range of the residuals. It's normally distributed. So the fact that if we look at this predicted value right here for this one, this x, if there's my prediction, it'd be a rare event for me to actually have a data piece that far out or actually have a data piece this far out. In fact, more of the time I would have data pieces that are closer to that predicted value and it will behave normally. Does that make sense? So we see kind of like, it's kind of hard because this normal curve needs to be in 3D.
Yeah.
Does that make sense? It's on its side, but it almost needs to be kind of coming against you this way. Okay? So that's extreme, and then we're going to have values that are closer to that predicted value. And so the standard deviation becomes a huge play on how good our linear model is. And that's what we're talking about with that error. And we did talk about this lightly in chapter 5. We called that SE, standard error. And if you guys remember the computer outputs that we had, a lot of the computer outputs talked about standard error. Back when we were at chapter 5, I had you guys memorize what standard error was. You're going to see it again in just a sec. Okay? Important statistics using linear regression. They are standard deviation of, I'm going to abbreviate least squares regression line, LSRL. Least squares regression line. The standard deviation of the least squares regression line is the thing I've been talking about here. It's abbreviated as SE. And we calculate that by finding the sum of the squares of the residuals. And notice we're talking about deviations. That is how far our actual data pieces are from our predicted data pieces. The sum of the square of the residuals over n minus 2. Notice that that is very similar to a standard deviation. Almost like it is a standard deviation. And it is. Clarify. SSR, sum of the squares of the residuals. This should make sense, is I'm going to say y minus y hat squared. So that's actual data pieces minus predicted data piece squared. And our calc does that, and there's a residual button on your calc, and I'll show you that in a second. This is a summation symbol. Okay. More words from the past. The coefficient of determination. How many people remember that word? Remember hearing it. How many people remember what that word means? You do?
I haven't tested it in the second.
What is it?
Depending on like how closely the two are related.
Good.
Close regards to one, close regards.
We had two. We had coefficient of determination and coefficient of correlation. We had Pearson's correlation coefficient and coefficient of determination. Now that should track you down to something. It's denoted by what? R squared or R? R squared? R squared. Coefficient of determination is R squared. Pearson's correlation coefficient, commonly called correlation coefficient, is just R. To get from R to R squared, we square it. To get from r squared to r, we square root it. R squared always has values between what? 0 and 1. R has values between what? -1, +1. So remember that. This one is R. The correlation coefficient. Is an R value of -1 good or bad?
Bad.
Good.
Well, we've got a 50-50 chance here. Some of you guys can guess good, some of you guys can guess bad. Is an R value of -1 good or bad?
Good.
Good. Is an R value of 1 good or bad?
Good.
Is an R value of 0 good or bad?
Bad.
Bad. How about an R squared value of 0? Bad. An R squared value of 1? Good. Okay? All right. R squared, here's your definition again. Gives the approximation, it gives the variation, I use the word typical. Variation in Y. The average, typical, whatever you want to use, it says, the textbook definition says the proportion, but if you look back in your notes, I said typical variation in Y. That can be explained by, I said can be explained, can be attributed to an approximate linear relationship between X and Y. And if you're one of the individuals who actually made vocab cards back when I said on chapter 5, find them, pull them out. This still falls under one of those definitions that you just need to have memorized. Okay? It can be calculated by, I'll give you the formula, I wouldn't worry too bad about the formula. Typically R squared is given to you, so you will not have to calculate it by hand, but it is 1 minus SSR, sum of squares of the originals, over SST, which is the sum of squares total. Again, I won't ask you to calculate that by hand, nor will they ask you to calculate it by hand on the SAT, on the
SAT.
AP. There's so many letters today. I'm all SSR, SST. And the sum of the squares total, if you're interested, is the sum of y minus y bar, which is the average squared. You don't really need to know the formula. So R squared's important. Way more concerned that you understand the interpretation of it and understand what these things mean, SE and R squared, and how it relates to the linear regression model, as opposed to I am the formula stuff. Here, right here, is y minus y bar. Because Stephanie's back today, I have another encouraging example for us. Because she always says we have the most uplifting examples in class. Infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ.
Hey.
So researchers explore the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. The researchers were snap a rubber band on the baby's foot and then measured the number of peaks in the baby's cry during the most active 20 seconds. They later measured the IQ at age 3. Here's the data in this table. So this is their IQ. No, that's not their IQ. That's their cry time. We're in trouble if that's their IQ. This is the number of, what was it? Peaks? Is that what it was? Peaks in the cry times over 20 seconds at 10. Their IQ at age 3 was 87. Remember, an IQ test is scaled 0 to 200, with 100 being the 50th percentile. That means if you score 100 on an IQ exam, you are exactly average IQ-wise.
And that 3-year-old got 150. 9?
Well, this one did. IQ tests aren't, an IQ test at age 3 is very different than an IQ test for a 13-year-old, which is very different than an IQ test for a 20-year-old, which is very different than an IQ test for a 50-year-old. Obviously, this 3-year-old did not take the test for a 20-year-old. Okay? So they have ways of extrapolating this kind of stuff. You've got another one. I believe anything over 160 is considered genius level. I will have to check that. Anything only over 160 is genius. It is reported, I can pull these out if you guys remember me through the class today. Madonna is reported to have a very high IQ. There's some, I'll Google it. At the end of class, last 5 minutes of class, remind me, and I'll pull this up because I don't want to misquote the numbers, but there's some people that have tested with high IQs. There's also a club. Have anybody heard of Mensa? All right. Remind me, last 10 minutes class, Mensa and IQ testing. All right, so here's what we want to do. This is the data that we're going to use. We need to input this into our calculators. So I'll give you guys a chance to go ahead and input that. It's much easier for me to input it on my small calc, so I'm not going to pull up the main calc on the board for this. And I'm going to pause the video while we're inputting. All right, in the notes, if you printed up the notes, it says draw a scatter plot. We don't need to draw the scatter plot. If you're looking at that linear regression model, you should have a line kind of drawn through there. We would probably predict, and you also probably have already looked at the R and the R squared values. The R values, just to remind you, I don't remember what that R value was, so I have it on there. 0.45? R equals 0.45, which we would, again, this is review stuff. We'd call that a weak, positive, linear relationship. You guys remember weak, positive, weak, negative, moderate, or strong? Weak, moderate, strong. Positive, negative. Well, R value just kind of a lot linear model. You can eyeball it. It's whatever you guys want. If they don't provide an R squared value, then you're going to have to eyeball it. Again, you could see that the line's going up. You could also see that our residual plot is probably going to have stuff all over the place because our actual scatter plot didn't look great. Do we agree with that? All right, part B here. In order to create linear regression, we already did that. What was our, I don't have it, I'll write it down here. You guys kind of agreed with me. We had this is our line of best fit. Y hat is equal to 91.2683 plus 1.4929, and that's X. Do we agree with that? And make sure you guys are okay with it both ways. That's with variables. Make sure you're also okay with IQ equals 91.2683 plus 1.4929 times the cry time. How many number of times that the baby cries after we hit it with rubber bands? Just for 7. 100 days back. Are you still not okay? What's that? Blank. I don't know. Remember that in order to create a linear regression line, we can use the, that's just the calculator directions. Stat, calc, we already did it. I can put it in there. Yeah. Now I was going to put the calculator language. You guys know the calculator language. Okay. Next thing I'd like to do. Create a residual plot. Do we remember how to create a residual plot?
Yes, we do.
We can do it by hand,
Let's not.
but I would suggest not doing it by hand. First off, you're going to need to clear your y value out there so you don't have an equation. And then you will need to make a scatter plot of your residuals. Okay. You probably already have your scatter plot turned on. X list, Y list. Your x-axis on your residual plot can be anything you want it to be. It could be your x, it could be your x values. It could be your actual y values. It could be your predicted y values. It could be any one of those three things. So you can choose what you want your x-axis to be. Right now, I have it just as list 1, which are my actual x values. And then your y values, you want that to say residual. So residuals are under second stat, under your list. You have a button there that says resid. Use it. So you don't have to calculate the residuals by hand. Back out of that, and then zoom 9 for stat fit. Again, my residual plot will be a mess there because this is not my data piece. But again, bring up your residual plot. All right. What you guys' residual plots look like? Let me see what you got. Who's go? Show me what you got.
Dots.
Flash me your residual plots. Diego, what's yours?
Diego's being lazy. Nah, dude.
Diego's been being lazy.
Where's yours?
All right. Next up. What are we looking for in residual plots? What are we looking at?
Whether it's random or pattern.
Random or pattern. Some people remember that from residual plots. We like a big messy residual plot. Big messy residual plots means we have a good linear model. If we have some sort of pattern, then we're going to say linear model is probably not the best model. Yes?
Is that the same for the regular scatter plot?
Not for the regular scatter plot, just for the regression plot. So, in this case, good residual plot, bad residual plot.
Good.
Good. So since residual plot is, I'll say, fairly scattered with no clear patterns, we will conclude that linear regression is an appropriate model, or that it is a good fit. A linear model is best. If we have patterns of the residual plot, what we want to say is a nonlinear model would be better. Appropriate. All right, we good?
No.
No. All right. Now, I'm going to this is our application stuff. That kind of finishes our review of linear regression. Everything that we kind of talked about for the last 40 minutes shouldn't have been new. Now, it should have been stuff that we covered and you may have been foggy, and it should be better now than it was. Okay? So, now I want to kind of go where we're going to finish up today. You'll see it on tonight's homework assignment and where we're going to go tomorrow. Next up is the centered error. A reminder that centered error is the square root of the sum of the squares of the residuals divided by n minus 2. we can calculate that one real quickly. And what I would do for that in my calc is just go to list, go to math. I want to sum my residuals squared. And that says sum of the squares of the residuals. It's going to be a big number. That's not, did you put the square there?
Second
Shouldn't be, that's not right. I didn't input that correctly. Maybe we gotta square the residuals first? I don't know. Oh, maybe, you know what? Don't put that, don't put the parenthesis. There we go, delete that. There we go. That'll do it. So again, it should be,
Whoa.
okay?
Yeah.
Okay, it should be a big number. Do not put
Where's the? We got 11,000.
some.
Okay.
I'll show you guys again how to do it. That parenthesis made a big difference. We need to do this. Go to your list, math, sum. You want the sum of the residuals squared. Okay? So this tells it, what I had told it was to sum the residuals first and then square it. I need to square my residuals first and then square it. So order of operations is why you guys were getting a 0. So there you go. That will be the correct answer. That should get you the big number. Okay? We're going to take that number. We're going to divide it by n minus 2. I'm just using the formula here. Divide it by n minus 2. N was the number of data pieces we had. I believe we said that was 38. So 38 minus 2 is divided by 36.
I got 306.
You're going to divide that by 36. My number's not right. And then you're going to square root it.
I got 17.49.
It should be something like that. It should be like 17 point something.
17.498.
17.498? Right there? 17.498? All right. Once again, definition, standard error. This value represents the average or typical deviation from each point on the least squares regression line. That's where I start out. That's that normal distribution I said around each predicted value. Okay? Value represents the average deviation from each point on the regression line. So, this is our extension. Now that we have an appropriate linear model, make a prediction. This is something you guys did back in your projects. What is the predicted IQ for a baby that had 16 peaks in its cry? You guys go ahead and figure that out right now. Again, what is the predicted IQ for a baby that had 16 peaks in its cry? How do we do that?
You plug it into the original formula.
You plug it in for x in your least squares regression line model.
The y equals
Y equals A plus BX.
Yes, that thing. That thing that we've all been talking about all day long.
What's a D?
Oh, really?
It looks a little weird at you.
Equals 150. What was the
Was 91.
So what?
No, that was me. A was 1.49. You want the long version? It was y hat equals 91.4683 plus 14929x. That's
Yeah. Yeah, I don't know now, so I don't know. Alright.
I got 116, 115.15. All right.
right. So
I want to show you something that's kind of nice. Yeah, calc's even better than trace. The calc button is even better than the trace button. Did you use the trace button? All right. Right now, if you would on your scatter plot, change it back to your linear regression, which is list 1, list 2. Back on your scatter plot, change it back to list 1, list 2. You can zoom stat that if you want, and you'll get your original scatter plot of your XY data. I would like you to rerun your linear regression. It's probably already in there, but just rerun it for the practice. So stat calc 8, and again, it's list 1, comma, list 2. Make sure you send the line there.
One, not this one.
Oh, thank you. That would have gotten me an error. List 1, comma, list 2, comma, and then send it, that equation to list 1, to the y1 value. Once again, you guys showed me that before. You guys had some linear regression model in there. I don't have no idea what mine is. I didn't have all those evidence, but you should have it. Now here's what I said. Yes? I'll turn that on for you in a second. Okay. All right. Right now, you should have this up, the line and your scatter plot. Here's the magic button. Press second, and then the trace button. You'll see that toggles the calc button. It's short for calculate. You would like it to calculate a value. The value you would like it to calculate is when x equals what?
16.
It's 16 right there, and it'll get you your answer. Mine won't get an answer. You guys will have an answer.
That's a beauty key.
115 point something?
Yeah, one.
Ben. What? Because that's what I asked you. Predicting. When a baby has 16 peaks, they should have an IQ of
This
115.
formula SSR divided by n equals 2.
That's for the standard data. That was for this part. We're doing right here. Oh no. Now this is the question. Let's predict IQ. With that one. Do we agree it's 115.15? All right. We are near the end, yes. We're near the payoff pitch. Now, a lot of things hopefully should come together. We know that this is a predictive model. We know that that is just a prediction based on our data points. We also know that reality, capital A plus capital B X, exists out there. But I know that my predictive model has this variation that varies normally about that coordinate. Does that make sense? I have a standard deviation of 17.49 that can go up and down around that predicted value. Does that make sense for actual data pieces that exist? So now we're going to answer this question. what is the probability that an infant who did have 16 peaks in his cry actually has an IQ greater than 125? Does that make sense? Do we see how we're now going to really apply this predictive modeling? Our data says that infant should have, that 3-year-old, when the infant had 16 cry counts, that 3-year-old should have an IQ of 115. If this is my standard deviation, and this is the predicted value, then what is the probability that a kid at the infant who had 16 cry counts actually has an IQ greater than 125? And watch this. Isn't that saying when my average is 115.15 and has a standard deviation of, what was it, 17.49?
Yeah.
What's the probability that that 3-year-old will have greater than 125 IQ? That looks really familiar. But remember what's happening in this case. This is that y value on the side. Do you see that normal curve that I talked about at the beginning of the day now? And what are we going to do here? It's just a z-score. Z equals 125 minus 115.15 divided by 17.49 something. Is that right? So we get a z-score. We can finish it up from here, hopefully. No? You make me die inside when you say that. Z-score? Or the actual answer? 2 point what? Yeah, something like that. What was your Z-score? 0.56. What'd you get?
0.286.
0.5626? What'd you get?
For my z-score.
What's your Z-score?
0.56.
How do you got a Z-score close to that? 0.5631? You said 7? Something like that? 8?
Technically, it should be around that.
Technically, it should be 0.563.
Okay. If 0.5632, you should be able to find that area. That's a norm. CDF, 0.5632, 100. And that gets you the probability that an infant, if an infant has 16 cry counts, by the time they reach age 3, according to this model, that they have an IQ over 125, was relatively rare. What was it, 27, 28? What was the percentage? Almost 29, so 28.28 what?
6.28.
So, do you see how now these linear regression models are going to start to really flirt with real-world applications? And yes, this was an actual study done. Yes, they used this data. No, it was pretend babies. It wasn't real babies. It was little Cabbage Patch Kids. And they gave them IQ test 3 years later.
Sorry, you show us.
All right. I think that's it for today.
For the product.
Yeah.